All right, good morning. I'm sorry that I can't be with you today. I'll be back tomorrow. Again, please be on your best behavior for the sub. We've got a few things we're going to do today. We're going to start by finishing up this notes page that we began last class, so it's page 35 in your binder. We did these drawings. We're going to start by finishing this up. So you need two things. First of all, find this paper in your binder. If you don't have it, please ask the sub for an extra copy. So do that first. The other thing you're going to do is at your table you should have a concepts and action book. So open your concepts and action book to page 114. So this out and open your concepts and action book to page 114. If there's time needed for this, the sub can go ahead and pause this video for you to get set up. All right, I want to briefly go over what we did yesterday. So we're talking about the history of our understanding of the atom. And we started here with Aristotle, who said that matter was continuous. Remember, we did the thing where we cut the paper in half and we cut the paper in half again, and Aristotle's idea was you could keep doing that forever. His sort of rival, the philosopher Democritus, thought that really matter was actually not continuous, that there was a smallest bit that you could have, and he called that, in Greek, he called those smallest bits that made up matter, he called them atomos. So that's where we get the name atom. And he said that atoms were these indivisible spheres and you couldn't get any smaller than that. He didn't really have any evidence for this, but several hundred years later, as a matter of fact, almost 1,000 years later, around 1800, the chemist named John Dalton came along, and he found evidence that things might be made of atoms like this. And the evidence was that if he took a compound and he measured the masses of the individual elements in the compound, he found that they were always in fixed ratios. And so he came up with, he gave credence to the idea that matter might be made of atoms. And it turns out if it weren't for John Dalton, chemistry as we know it today couldn't exist. And our understanding of, anything chemical, it just would not exist if we didn't have John Dalton. But John Dalton again thought that the sphere, the atom was an indivisible sphere. You couldn't get any smaller than this. And at this point, I'm going to just come over here to your book. This was John Dalton's model, that it was an indivisible sphere. You couldn't get any smaller than that. But then this guy named J.J. Thomson came along, and he was dealing with cathode rays. And remember, we did a demonstration with a cathode ray yesterday. And he found that if you put magnets next to these cathode rays, you could change the direction they were pointing. And so he reasoned that the ray had to be made of charged particles. And he did other experiments to prove that these were very light charged particles, which he named electrons. And so he thought that Dalton's model needed to be improved. So J.J. Thomson's model, which we call the plum pudding model, he said that the atom was a sphere, but it was a sphere of positive charge that had these negative electrons sort of scattered throughout it. And that was his model, the atom. He was right about a lot of things. He was especially right that there are electrons in an atom. But the next person to come along that we talked about was Rutherford. And remember, we did this thing, and I'm just going to turn back real quick because I just think it's a good diagram. Back on page 104, he did this thing where he had a beam of these alpha particles, which are just essentially really tiny positively charged particles, and he tried to shoot them through a piece of gold foil. and he expected them all to just go through. But some of them bounced back, and he was trying to figure out why they bounced back. And the way that he reasoned that they bounced back was that there must be a really dense center to these atoms, which he called the nucleus. And when the particle hit the nucleus, it would bounce in pretty large angles. And if it didn't hit the nucleus, it would just go straight through. And so, going back to page 114, Rutherford's model of the atom has all of the mass, or most of the mass, here in the center in the nucleus, which was positively charged. So it's just like Thomson's model, except now he says that all that positive charge is in the center, and that the electrons just sort of whiz around the outside. And so this is Rutherford's model, and that's where we ended up. We ended up with Rutherford's model. Well, you can see as you go on that we go a little bit farther with this, but I want you to just turn back a page, and I'd like you to start by reading this section about Bohr's model of the atom, and then the section about energy levels. And I basically want you to read all of 113 and page 114 and 115, and then you can stop at the bottom of page 115. The sub's going to give you about 5 or 6 minutes to do that, and pause the video while that's happening. Okay, so hopefully the video has been paused now, and now we're back playing. And what I'd like you to do now, we're going to talk about what was new about Bohr's model. Well, Bohr realized this idea of energy levels, which we read about here. Energy levels are, he basically found that there are certain energy levels that an electron can have. And the way he figured this out was, it turns out that there are certain things that happen when electrons change energy levels, and we'll talk more about that. But he found that all atoms did this, where their electrons could only be in distinct energy levels. And so here we go to Niels Bohr's model of the atom. So that's Neils. There's actually no apostrophe. Niels Bohr. And his evidence was, he found that the electrons can only exist in certain energy levels. Now, that's a fact, right? There are experiments you can do to show that electrons can only exist in certain energy levels. But what you have to do is you got to use your imagination to get sort of a what he did was he uses that imagination and said, well, why do they have certain energy levels? And he said that it was because electrons can only orbit the atom at fixed distances. Electrons can only orbit the atom at fixed distances. And so you see that picture there in your book, but essentially the way we're going to draw that is we still have the nucleus that Ernest Rutherford had, but the electrons, instead of just whizzing wherever they want, they can only be like either at this radius or this radius or this radius. So it's sort of a more neat and tidy version of Rutherford's model of the atom. Okay, so that's the Bohr model of the atom. Now, Bohr got a lot of things right. This idea of energy levels is true. However, there are a couple things that we learned, and basically there was a scientist named de Broglie. You don't have to know this, but there was a scientist named de Broglie who said that electrons can behave like waves. And then there was a guy named Erwin Schrödinger, and Erwin Schrödinger, which you may have heard of Schrödinger's cat, but Schrödinger then came up with what is called the electron cloud model. So basically, Schrödinger is just a little bit more complicated of a version of Bohr's model. So electrons can only exist in certain energy levels, but it turns out that Schrödinger, it's essentially just a mathematical thing, so it's hard to draw. So Schrödinger learned how math could describe energy levels. And so we call these, the mathematics that describe these are more complex than just these simple circles. So instead of the electrons orbiting an atom at a fixed distance, the electrons exist in what's called an electron cloud. Exist in a cloud. And it's just the way that I would draw it is kind of like this. And what happens is, even though it's a cloud and it's really hard to draw, it turns out that the mathematics are actually very specific in terms of what this cloud means. It's a little bit beyond the scope of what we're going to do, but that was Schrödinger's idea. And then we just have to finish it up with a guy named Chadwick. And Chadwick discovered that there are, he basically discovered neutrons. So he discovered neutral charge particles, neutrally charged particles, which we now call neutrons. And so in his model, which is basically the model that we have now, the nucleus has positive protons and neutral neutrons. So the way I'm going to draw this is, I'm going to draw, let's say here, two protons which have positive charge, and then I'm going to draw two neutrons which have negative charge, and they're here in the nucleus in the center, and there's still the electron cloud. That Schrödinger had. But what I want you to realize is that this is just, it's not that these scientists up here were wrong. It's just that we learn more and more. Aristotle does a good job of explaining why I can cut a piece of paper 1,000,000 times, right? So when things are big enough that we can see, Aristotle does a really nice job. But when I start getting really small, we need to improve on Aristotle's model and come up with the idea that there are these things called atoms. And then when we start dealing with cathode rays, we learn that not only are there atoms, but the atoms are made of different things, like electrons. And then we find that the positive charge, instead of being spread all the way throughout the atom, is just in the center. Then we learn that the electrons have fixed energy levels, and then we learn the math behind the fixed energy levels. And then we learned that not only are there protons, but are there neutrons. So what we're doing is we're essentially building on this model. We're learning more and more about this model as time goes on. So it's not that these models up here are wrong. They're just incomplete, and we learn